If you would recall, yesterday we started looking at optimization, and we're really just updating this procedure that we learned way back in Calc 1. We take the first derivative, set it equal to 0, and solve, and then use the second derivative to classify each critical point as a local minimum, a local maximum, or neither a local minimum nor a local maximum. We know that there are certain situations where the second derivative will not tell us what's going on at the critical point. In particular, if the second derivative is also equal to 0, then we don't know what's going on. We have to do something else to classify that critical point. Yesterday, we found out that the procedure is largely the same. We take the first derivative, set it equal to 0, and solve to find the critical points. And then we use the second derivative to somehow determine if those critical points are local minimum, local maximum, or neither. Yesterday, we looked at very straightforward examples where our intuition about the second derivative and what it tells us about concavity went really well with the example that we looked at. But we needed to generalize that. We also want to bring in some of the other ideas that we have about first derivatives, especially with partial derivatives running around. Any questions before we get started? All right. So in particular, let's bring up the first derivative, take the first derivative, set it equal to 0, and solve question. Now, I wrote it different today. Today I wrote solve gradient f equals 0 to find the critical points. This is equivalent to say, set the first two partial derivatives equal to 0 and solve it. The gradient of f is the x derivative in the I direction and the derivative with respect to y in the j direction. So if the gradient of the function is going to be equal to 0, that means each of those components must be equal to 0. That is equivalent to saying fx equals 0 and fy equals 0. So saying the gradient of f is equal to 0 is saying that both first partial derivatives of f are equal to 0. This should match with what we know. This should match with what we understand about the gradient. We know that the gradient indicates the direction of maximum increase or the direction of maximum decrease. So it makes sense that the gradient is going to be equal to 0 at a point where it's the highest point, because all there's going to be is decrease at a local maximum, and it's the same in all the directions, in any direction. We're going to have the same direction of maximum increase or the direction of maximum decrease. We can't pick one direction and say go that way, it's steepest, because we're at the bottom of a trough or we're at the top of a hill. In any direction will be appropriate. So it does fit in with our intuition about what the gradient is supposed to tell us. Mechanically, stating that we find the critical points by setting the gradient equal to 0 is the same as taking the first partial derivatives and setting them equal to 0 and solving that system of equations. So mechanically, it makes sense. It makes sense with our intuition about how we think about the gradient. Now all we have to do is classify the critical points with the second derivative. The trick was there are 4 second derivatives. So that's what we need to talk about today. How do we use all four second partial derivatives to classify at a critical point? So first, we need to define a particular function. We need to set up a discriminant. So we're going to define this function, d of xy to be fxx times fyy minus fxy squared. Note that this seems to only involve three of our four partial derivatives. If our function is going to have continuous second partial derivatives, then fxy will be equal to fyx. Those two derivatives will meet. If we're going to have continuous functions, which we need for all this to work out, then fxy will be equal to fyx. I'm paraphrasing, but f continuous as long as we're going to have continuous partial derivatives, then fxy will equal fyx. So it makes sense just to take fxy and square it. Now we need to think about how we read this quantity. There are a few things that can happen. This quantity can be positive, this quantity can be negative, this quantity can be zero. We're going to read this d function similarly to how we read the second derivative, positive, negative, zero. Any questions while I blank out for a second? Apparently at this point. All right, so let's think about where this comes from. This is the structure here is actually like a discriminant. We're doing an AB minus a BC type of thing. So it's like we're calculating, the determinant of a matrix. So we can read this as the determinant of fxx, fyy, f. I can't remember if I want fxy here, fyx. I can't remember my order. So we're calculating this determinant. Now, I actually need to look something up. So I'm trying to summarize, and I know it's here somewhere. All right, this is what I, for some reason, can't seem to remember. Let's take a look at how we're reading what's going on with this D function. If D is positive and fxx is positive, then we have a local minimum. If D is positive and fxx is negative, then we have a local maximum. This, in part, makes it seem like we're reading the second derivative positive, local minimum, second derivative negative, local maximum, but we're only looking at one of our four second partial derivatives, fxx. In fact, we could also state this using fyy as being positive or negative. The reason that we only need to read one of those is that opening statement, or that opening piece. If D is positive and fxx is positive, then if D is positive and fxx is negative, let's think about what that means. If D is positive, well, let's write that down. If D is positive, and fxx is positive, then local, that second derivative positive means concave up, local minimum. Then the second part said, if D is positive and fxx is negative, then local maximum. So it looks like we're making the decision based only on fxx, and we should be concerned about all four. Here's where we're concerned, where you can see the concern about all four. If D is positive, so if D is positive, this is making the signs of fxx and fyy the same. So notice that when we say D is positive, that means fxx and fyy must have the same sign because of what we're calculating. So because D is positive, this part right here this will mean fxx and fyy have the same sign. Because I take fxx times fyy and then I subtract something from it. Fxy squared, that's going to be a positive quantity, we're subtracting. So if fxx and fyy have the same sign, then D could end up being positive. If D is positive, then most definitely fxx and fyy have the same sign. We're subtracting from a positive quantity. That's why I only have to look at fxx, not fxx and fyy. If D is positive and fxx is positive, since D is positive, we know that fyy is also positive. That's why we only have to list one. So if D is positive, then fxx is positive. This also means fyy is positive as well. Because fxx and fyy have the same sign when D is positive. Similarly, in the second line, if D is positive, that means fxx and fyy have the same sign. And so if fxx is negative, then fyy is negative as well. So D positive means they have the same sign. Let's think back to the examples that we built up yesterday. Fxx is positive, so we could read that as concave up in the x direction. Fyy is also positive, so that means we have concave up in the y direction, and that's giving us a local minimum. Similarly, concave down in the x direction, concave down in the y direction. It looks like we're going to have a local maximum. D being positive means Fxx and Fyy have the same sign. Note that I'm multiplying Fxx and Fyy. If I calculate D, since I multiply Fxx and Fyy, if I come out with a negative value, that most likely means that Fxx and Fyy have opposite sides, because that first term will be negative, and we're subtracting something from it, making it more negative. So if D is negative, I spelled less than. I was thinking about the next line. Notice that when we look at D less than 0, we don't have to look any further. If D is negative, then we can just go right to saddle point. You must be looking at a saddle point. If D is less than 0, then we have a saddle point. Most likely it's because the most likely reason that D is negative is that Fxx and Fyy have opposite sides. Concave up in one direction, concave down in the other direction. And that's what makes a saddle point. We have a local max in the x, but a local min in the y. So most likely the reason for this is that Fxx and Fyy have different sides. Because if Fxx and Fyy have different signs, then this D calculation will definitely be negative. Graphically, what that means, concave down in one direction, concave up in the other direction, that's what a Pringle is made out of. So if D works out to be negative, then we definitely have a saddle point. You might notice that if Fxx and Fyy have the same sign, but the quantity is very small, and we just subtract off this Fxy at that point, it just happens to be abnormally large. That's another way that D might be negative. So that's definitely something to keep in mind. But if we have two different directions, two different concavities at the one point, that's what makes the saddle. Now this only covers 2 out of 3 cases. We've got D is positive, we've got D is negative. The other thing that can happen is that D can equal 0. And if D is equal to 0, then we get nothing. If D is equal to 0, anything can happen. What that means is that we have to do something else. So if you use the second derivative test to classify a critical point, and you calculate D and it works out to be 0, then you have to do something else. So if D is equal to 0, could be anything. But you have to do something else to figure out what that is. You can't just write, well, the second derivative test was inconclusive. Think back to the ratio test when you were determining if a series converges or diverges. The ratio test said if this limit is greater than 1, if this limit is less than 1, or if it's greater than 1, then the series diverges. If it's less than 1, then the series converges absolutely. And if the limit from the ratio test is equal to 1, you get no information from the ratio test. That doesn't mean that we can't tell if the series converges or diverges, because it definitely does one or the other. But the ratio test is not going to tell you. So if d is equal to 0, then could be any one of these three things. If d is equal to 0, this just means we have to do something else to determine, to classify the critical points. So that just means that we have to do something else to classify that critical point. This is just a multi-dimensional second derivative. What's the second derivative? This also gives us some insights as to how this should work if we have a function of 3 variables, because we should follow a similar strategy if we have a function of 3 variables. We have a function of x, y, and z, then we're going to have 3 first partial derivatives. And we should still want the gradient of f to equal 0, because I'll have our 3 first partial derivatives equal 0. So the function will be flat in all 3 directions. We're looking for points that are where the function is flat in all 3 directions. But if we have 3 first partial derivatives, how many second partial derivatives are we going to have? So fx, that's 1. And that is still a function of x, y, and z. So that will also have 3, that will produce 3 second partials. fxx, fxy, and fxz. Fy will also have 3, and fz will also have 3. So I have a total of 9 second partial derivatives. So we'd have to make some kind of new function for d that combines all 9 of those second partial derivatives so that we can read positive. Is concave up, which means minimum. Negative is concave down, which means maximum. Different directions would mean a saddle point. We'd also have to think about what a saddle point would look like for a function of 3 variables, and it's very difficult because we're talking about a 3-dimensional solid in 4-dimensional space, and it's just hard of a picture. But still a question that we might want to answer. Any questions? It's important, this last one, the do something else part is important. As the first time you ask students about the ratio test, if you give them some, or ask about convergence of series, if you give it as once you do the ratio test, everybody wants to just use the ratio test. Then if you have a rational or a radical function, the ratio test gives you a value of 1. And sometimes you're just in such a ratio test verb, you write inconclusive. And that's just That's the same as leaving the question blank. You know what I mean? Any questions? Comments? Deep thoughts? How's everybody okay? Hopefully everybody's better than me. Show up to class late. Totally threw me off. Can't remember simple things like this. Second derivative test for function of two variables. Who else? I don't know what's worse, forgetting the second derivative test for functions of two variables, or like when I walk into a room and forget why I went into that room. I don't know which one's worse. So you'll notice that I assigned homework from chapter 15. We just have to take set the first derivatives equal to 0 and solve. And then now we know how to use all four parts, all four second partial derivatives to classify our critical points as minimums, maximums, or saddle points. The only real tricky one is going to be if d is equal to 0, where you're going to have to do something else to figure out what kind of point you have. You just look nearby, see if it's bigger than all the rest. So tomorrow we need to look at one more extra piece of optimization. We're not just going to try to maximize and minimize a function. We're going to maximize and minimize a function subject to some constraint. So I think the one that's most often used is saying maximizing profits. If you want to maximize profit, just sell an infinite number of widgets or whatever you have to be selling, and you'll have infinite profit. But clearly that's not possible. There's some fixed constraint to the number of widgets we can produce and how we produce them. So we might want to know what the optimal solution is. Other examples, if we're going to use some fence to build a pen, and we want to enclose the maximum amount of area. With no constraints, we would just say, make the pen infinitely large and it will enclose an infinite amount of area. But usually there's going to be some fixed constraint that keeps us from just using an infinite amount of fence. So subject to a certain amount of fence, that's going to be a constraint. Any questions? Comments? Snide remarks? All right. I know I started late, but I'm also have to cut out early because clearly I forgot what I was going to talk about today. Who can explain these things? All right, that's going to do it for today. I will see y'all on tomorrow. Everybody have a good day. And thanks for playing.